Hello everyone, and welcome back to the channel. In our last video, we explored the machine instruction cycle and saw how mnemonics make opcodes easier to read. Now we'll examine how high-level code becomes machine instructions that a CPU can execute. When a program is written in a high-level language like C, it first goes through a compiler. The compiler translates this code into assembly language, a low-level human-readable form. Then it converts the assembly into binary machine code that the CPU can run directly. This multi-step process allows high-level languages to create efficient programs that run smoothly on hardware. Most modern compilers skip generating assembly and go straight to machine code. However, many compilers like GCC still offer options to produce either assembly or machine code, giving developers flexibility. Consider this simple statement written in the C programming language. Suppose we wish to program this in machine language where I and j are 2 and 3 respectively. Suppose the program starts at memory location 200, and memory is reserved for the 3 variables starting from location 300. The program would consist of the following steps. First, load the contents of location 300, which is I, into the accumulator. Second, add the contents of location 301, which is j, to the contents of the accumulator. Third, store the contents of the accumulator in the location 303. The program would look something like this. The first field represents the address of the instruction. The second field represents the opcode, and the third field represents the location of operands. This is difficult to read and error-prone as the memory locations are hard-coded. The opcode and the operands are all written in binary, making it challenging to handle. It would also make any changes in the program difficult, as this will change the addresses of all the other instructions. A much better solution would be to use mnemonics instead of the opcode and symbolic addresses instead of hard-coded addresses, as shown here. Instead of using binary opcode, we use human-friendly symbols. The first field still denotes the address, but a symbol is used instead of numerical values. Some rows do not have addresses, which means they are calculated relative to the last row, which has the address. The third field contains the names of operands and not their location. When we make these changes to the machine code, we have an assembly language. Now let us look at a Hello World program written in assembly language. There are different types of assembly language for different hardware. For this example, we will use NASM, which is used for the x86 architecture. The given NASM code is a simple program that prints the string Hello World to the console using the Linux system call interface. Let's break down the code step by step. The first line is a directive. A directive in assembly language is an instruction that guides the assembler on how to process the program but doesn't translate into machine code itself. Directives are used to define data, organize code, and control the assembly process. This directive specifies the section where the data will be stored. In this case, the data is in the next line, the string Hello World, defined as a byte array, represented by db, with a null character at the end, represented by 0ah. Next, we have another directive that specifies the section where the code will be stored. In this case, the code is the main program logic. The global start directive makes the start label globally accessible, allowing the operating system to know where to start executing the program. The next line, _start, is the entry point of the program. It is where the execution begins. Move EDX13 instruction moves the value 13 into the EDX register. The value 13 represents the length of the string Hello World. Move ECX MSG moves the address of the MSG variable into the ECX register. The ECX register is used to pass the address of the string to the system call. Move EBX1 moves the value 1 into the EBX register. The value 1 represents the file descriptor for standard output, usually the console. Move EAX4 moves the value 4 into the EAX register. The value 4 represents the system call number for writing to a file descriptor. Int ADH triggers the system call. The operating system will execute the corresponding system call based on the value in the EAX register. Move EBX0 moves the value 0 into the EBX register. The value 0 represents the exit status of the program. Move EAX1 moves the value 1 into the EAX register. The value 1 represents the system call number for exiting the program. Int ADH again triggers the system call. The operating system will execute the corresponding system call based on the value in the EAX register. As we can see, writing a program in C is much easier and simpler compared to writing it in assembly language. The compiler and assembler allow the programmer to focus on writing the program logic and not worry about the underlying hardware operations. After the assembly code is generated, it goes through the linking phase before an executable code is produced. Linking is the process that combines various object files and libraries into a single executable file. Here's how it works. During linking, the linker examines all symbols, like function names and global variables, in each object file. It then tries to resolve them by matching each symbol's definition to its use. For example, if main.o references a function foo defined in foo.o, the linker connects the call in main.o to the actual code in foo.o. This is called symbol resolution. Next, the linker calculates the memory addresses for each segment of code and data in the final executable. Since object files were compiled without knowing the final memory locations, the linker updates the addresses of instructions and data to reflect their final positions in the executable file. This is called relocation. After relocation, the linker may also bring in external code from libraries, such as the C standard library, to fulfill any external references that are still unresolved. Static libraries like .a or .lib files are directly included in the executable, while shared or dynamic libraries like .so or .dll files are simply referenced in a way that loads them at runtime. In programming, a library is a collection of pre-written code that developers can use to optimize tasks and add functionality without rewriting common routines or functions. Libraries contain compiled, reusable functions, classes, or resources that can be included in various programs to perform specific tasks or add features, making development faster and more efficient. For example, standard libraries come bundled with a programming language and offer essential functionality for basic tasks. These libraries provide support for tasks such as string manipulation, file I/O, mathematical computations, and data structure operations. In C programming language, stdio, math, string, etc. are all standard libraries. Static and dynamic libraries are files that contain reusable code to help streamline development. They both offer a way to include external functionality in a program, but they work in different ways regarding when and how they are integrated with an executable. Static libraries are files that contain code that gets compiled directly into an executable file. Once compiled, the code in a static library is embedded within the program's executable file. Static linking is often used when distributing software that needs to be self-contained, as the library code is embedded in the executable. In Windows, static libraries typically use a .lib file extension. In Linux, static libraries typically have a .a file extension, which means archive. The resulting executable is self-contained and doesn't depend on external libraries at runtime. Dynamic libraries, in contrast, are not embedded directly into the executable. Instead, they are linked to the program at runtime, meaning the program relies on external files for the library code. Dynamic linking is often preferred when multiple programs need to share the same library, as only one copy of the library needs to be stored in memory, making it memory efficient. In Windows, dynamic libraries have a .dll file extension. In Linux, dynamic libraries typically have a .so extension. Dynamic libraries are memory efficient because the same library can be loaded into memory once and shared by multiple programs. Finally, when all references are resolved and addresses are set, the linker produces a single executable file, typically an exe file on Windows or an elf file on Linux. Once the linker has finished its job, the executable file is ready to be loaded and run. The loader performs this job. Here's how it works. The operating system's loader takes over when you run the executable. The loader reads the executable file from the disk and loads it into the appropriate memory locations in RAM. During loading, the OS sets up the memory space for the program, dividing it into sections such as code, data, heap, and stack. Modern computers use a logical memory layout that includes segments like text, data, BSS, heap, and stack while executing programs. However, this segmentation is largely logical rather than physical. These segments are not isolated into strict physical regions. Instead, the operating system and memory management unit, MMU, manage these sections virtually, mapping them onto physical memory as needed. If the program relies on shared libraries like dynamic link libraries or shared objects, the loader locates and loads these libraries into memory too. It then resolves any remaining symbol references between the executable and the libraries. The loader may also perform runtime relocation if the program relies on shared libraries. adjusting the addresses in the executable to match the actual memory locations where the libraries are loaded. This step is necessary if the code or data segments need to be loaded in a different location than originally specified by the linker. This usually happens when the memory address space where libraries reside is shared among multiple programs, so they need to adapt their addresses as they're loaded. Once the executable and any libraries are in memory, the loader sets the program counter to the entry point of the program, usually the main function in high-level languages. At this point, the CPU begins executing instructions, and the program officially starts running. The operating system manages the process's memory and resources throughout its execution. In summary, linkers and loaders are vital for creating executable programs from source code. They handle the complexities of combining multiple files, resolving symbols, and managing memory, allowing developers to focus on writing code without worrying about the underlying details of how it all comes together at runtime. This functionality enhances modularity, promotes code reuse, and facilitates efficient memory management in computing systems. Thank you for watching the video. I hope you learned something today. Have a beautiful day and see you in the next video.